All right, so in this lecture, we're going to work through the first note guide of Chapter 8, and this is going to go over 8.1. And what it gets at is this idea of how torque affects equilibrium. So before, we always had a particle model with all of our forces acting from the center, and it was good enough just to balance the y and x forces, or x and y forces, and we were in equilibrium. But now with an extended object where the forces can act from different points and it matters where the force acts from, we create this idea of torque happening. And in order for an object to be in equilibrium now, the x forces still have to balance, the y forces still have to balance, and now the torques have to balance. If we choose a pivot that's different, then like if I chose a pivot for a problem that was different from what you chose, the torques will calculate differently. However, if the object's in equilibrium, then it doesn't matter where you picked the pivot to be and where I picked it to be. The net torque will still equal 0. And that's an important concept here for this chapter, is that you can choose the pivot so that it benefits you in the problem, and you should pick the pivot to be somewhere where maybe, usually it helps where you say you have a force you don't know, you'd put the pivot there. And the idea behind that is, well, any forces through the pivot cause 0 torque. So by putting the pivot somewhere where you don't know a force, it simplifies the problem. Sometimes the pivot will be an obvious place because it's a place where there naturally just is a pivot and it would make sense to put it there. But other times it doesn't make sense, or you're kind of guessing, and just put the pivot somewhere that would help simplify the problem. And that would mean somewhere where you have an unknown force. And I think we'll see an example of that at some point in this note guide. All right, so this first example is what we have here modeled is a human arm, and a person doing a barbell curl. This is their bicep, this is their forearm. The bicep muscle is attaching here into their forearm. This is the elbow where we have the pivot happening. So this is kind of a natural pivot, so we really don't have to worry too much about that. We're just going to put the pivot right there. And you can see we have 3 forces here. The force of the elbow, which is actually downward. And I didn't expect you to know that one's there. The force of the bicep muscle, which is attaches on the forearm and pulls up. So that's going to be right here. And then the force of the barbell that you're holding on to pulling down. Now this is a 900 Newton barbell, and one of the tricks of this problem is just realizing that this is just one arm, so the force of the barbell in one arm is going to be 450, the force of the barbell in the other arm is 450, using both hands to curl this barbell. All right, so they tell us that the distance from the elbow to where the tendon attaches is 4 centimeters, so that's going to be 0.04 meters. Just make a little correction there. This is looks like distance to the barbell, which is going to be this distance right here, and that's going to be 35 centimeters, so we're going to say 0.35 meters. You know, we don't like to work in centimeters. And so what we're going to do, or what we want to know here, is what is the force of the tendon pulling up, right? And then what is the force of the elbow pushing down? And to find those two, we're going to balance our 3 things here. Our forces in the x direction, forces in the y direction, and torques. So right away, we can balance the forces in the x direction because there's no forces in the x direction. So we can, we don't even have to write it, but we can say very simply already that the sum of the forces in the x direction is equal to 0, but there's no way to elaborate there, right? So we're just going to leave that just like that. We wouldn't, I probably wouldn't even write that at all, right? But I'm just pointing it out. I'd say the torques are usually toughest, so I usually start with the X and Y forces first. I'm trying to see. It says, what is the tension in the tendon connecting the body? Okay, so I'm not going to worry about that right now. I'm just going to just go through the process, right? The process of going this way through the X forces, the Y forces, and then the torques. So let's look at the Y forces next. So we can go ahead and say the sum of the forces in the Y direction is equal to 0 because the object is in static equilibrium. But now we can expand on that, right? We have a Y force here in Ft, a Y force in force elbow, and a Y force here. This one being positive, so we're going to say Ft is up, make that positive, minus force elbow being down, minus force of the barbell is equal to 0. We don't know the force of the tendon, so we'll just leave it as Ft. We don't know the force of the elbow, but we do know the force of the barbell for one hand, right? And we're just looking at one hand right now. Our one arm is going to be 450 newtons. All right, so so there we have it. That's as far as we can go in the Y direction, and now we are stuck, right? So now we have to turn to the torques and work with the torques. So we'll leave that right there, and we'll go to sum of the torques. I hope I have enough room here. I guess I'll work right here. So we can say the sum of the torques is equal to 0. Remembering that, let's look at these forces individually. So we'll start with force of the elbow. Force of the elbow goes through the pivot, so this does no torque, right? So if you were thinking it did, you would just write, well, actually it would be kind of hard to even, the R value or the distance would be 0 because torque equals R cross F, or RF, sine 90. But there's really no R value here, so that would be 0. So you'd multiply the force of the elbow by 0, and then I would have a hard time labeling this as positive or negative because it doesn't really point counterclockwise or clockwise to the pivot, right? Okay, so anyways, this is 0. So torque of the elbow is 0. Torque due to the tendon, right? Well, what is that going to be? Well, here's my pivot. So this force is going to cause it to rotate. Whoops. This force is going to cause it to rotate like this. And so that would be a counterclockwise torque. So we think of that as a positive torque. So I'm saying that the torque of the tendon is going to be positive. And then the torque due to the barbell, here's the pivot again where my finger is. So once again, this one would torque it this way. So that's going to be clockwise or negative. So we can say the torque of the barbell is equal to 0. So that we already labeled this one positive, this one negative. Now we can say, well, here's our R value, right? So the torque due to the tendon is going to equal, it's RF sine 90, because both of these are perpendicular already, so these are very easy to find torques for. So we can say that the torque due to the tendon is equal to the distance to the tendon times the force of the tendon times the sine of 90. And likewise, don't forget your subtraction sign. We can say the same here, except this is going to be distance to the barbell, right? It's all about the distance from the pivot times the force of the barbell times sine 90. Now, is it always sine 90? No. And we're going to see that in some of our problems going forward. Sometimes we'll have to use cosine. Sometimes we'll have an angle. It's not always going to be that nice, so don't get used to that. All right, so we can go ahead and label these values in. Distance to the tendon is 0.04 meters. Force of the tendon we don't know. Sine 90 we know is 1. All right, both of these are just going to become 1. All right, distance to the barbell is 0.35. Force of the barbell is 450. We're just looking at one arm. And now you can see this is something we're going to be able to solve for and get the force of the tendon. So let's go ahead and get that 0.35 times 450, which is equal to 157.5. Units here are Newton meters. And this is going to be 0.4 meters, or sorry, 0.04, geez, 0.04 meters times the force of the tendon. Kick this over the other side, divide by 0.04. All right, we can see that our meters are going to cancel. We'll type this in the calculator. 3,937.5 newtons, which is quite a lot. So it's interesting here that to lift a 450 Newton weight, the amount of force that's required on the tendon of the bicep muscle is 3,937.5 newtons. So I think it's very inefficient to have this tendon attached right here. That if in a human's arm, if the bicep muscle was attached further down, we would increase this distance and make this more efficient, and it would be easier to lift weights. But this is the way our arms are designed, and that's, yeah, that's what we got. So all right, let's get the force of the elbow here. So if the Y forces have to balance and we have this large force, we're expecting the force on the elbow pointed down is going to be pretty large. So let's go ahead and plug now this, or sub this into there. So we get 3,937.5 newtons minus the force of the elbow minus 450 is equal to 0. So this is just a little math here. We'll add this to the other side, subtract this, and then divide. That's kind of gross. Let's just go ahead and kick force elbow over there. That'll make it positive, and then we'll just take this minus this. That's easier. So I'm saying we're going to have force elbow is equal to 3,937.5 newtons minus 450. And then we'll just do the math there. That's pretty simple. I could probably do it in my head, but not really feeling it right now. 3,937.5 minus 450, 3,487.5 newtons. And that's the magnitude. We know that that force is directed downward, so that's just the magnitude right there. Okay, that's it. So pretty straightforward there. All right, let's look at the next example. All right, so in this next one, this is a stop to think question, and what it's dealing with here, what the question says, is which of these objects is in equilibrium? And we now know that there's 3 checkoffs here, right? The X forces have to equal 0, the Y forces have to equal 0, and the torques have to equal 0. So let's go through these and look at these in terms of X and Y forces, and then maybe torques as well. Now, a good question here is, where is the pivot? Well, the pivot is right in the middle of the object. And I forget if the book tells you that, and I just forgot to include that. But that's kind of the idea. So anyways, on this first one, do the X forces balance? Well, we can say this one in the middle would balance this one, but then we have this X force to the right, so no. So this would have a net, I'm trying to think of how I should write this. This would have a F net in the positive X direction, right? This here is not going to be in equilibrium without even looking at torques. If we looked at torques here, we could see, and there's no Y forces to balance, so we don't have to worry about that. Well, if we looked at torques, this force is through the pivot, so it does no torque. This force is through the pivot, so it does no torque. But this one would torque the object, right? This is not through the pivot, so there is an R value here to work with. All right, so we know for a fact then that this is going to be wrong, right? Okay, let's go to the next one. Here, once again, X forces don't even balance, right? So immediately wrong. Do torques balance here? You should say yes. This force does no torque. This one does what kind of torque? Clockwise or counterclockwise? Let's see, if you pushed here, it would cause it to spin like this. So this top force would cause it to rotate this way, clockwise. This bottom force, counterclockwise. Torques would balance here, but there's still a net force in the, so this, in the X directions. This would have an F net, comma, X. So this is wrong. But in this one back here did have a torque net. And that was, let's see, because of this, so this would be a clockwise. So this would be a clockwise torque net, or it would be a negative torque net. So that's wrong. Answer C, here, I think my drawing is kind of crummy, but this plus this should equal this is kind of the idea, right? This is just kind of a bad drawing. So the X forces do balance here. So that's a good start. Y forces balance, there's no Y forces. What about torques? All right, and this is where it's definitely not gonna work. There is gonna be a torque net. Can you see which direction? Take a guess there, which direction? Counterclockwise or clockwise? And you should say counterclockwise, right? Because these two balance, but then this is gonna cause it to torque and spin, right? If this is the box, it's gonna spin like this. By pushing here on this edge, it's going to turn it this way about this pivot. So if that's the case, then we're saying a counterclockwise torque net or a positive torque net. So this is wrong. All right, so this has to be the right answer. Let's look at why. First of all, X forces, do they balance? Yes, right? 2 to the right, double to the left. Torques, do they balance? This one goes through the pivot, so no torque. And yes, in this case, this one would do a clockwise torque. This would do a counterclockwise torque of equal magnitude. So this is our correct answer. All right. Then I went ahead and gave you down below the process of going through the problem, similar to draw a free body diagram, pick the pivot point. That's super important because you want to pick one that simplifies the problem, then balance the X forces, balance the Y forces, balance the torques. This is outlined in the book, but I just put it here in the note guide too. All right, let's go ahead and take a look at example problem 2. Okay, so in example problem 2, we have a board sitting on a couple sawhorses. Sawhorses are exerting upward forces that we don't know. And this is an extended object, so we cannot assume that all the forces act from the center, and instead the forces act from exactly where they are. So what are the forces here? First step would be draw the free body diagram. It's a 3-meter board. It's symmetrical. So if it's a 3-meter board, then we know that at, I guess I can use the red pen, at about halfway here, right here, is the center of gravity. And from there acts the force of gravity, which is going to be Fg of the board. I don't know if I need a comma board there. I think we're good. So Fg acts there, and then we know force normal. We have 2 of them, right? And we have one acting here. I don't know which one's larger, so I'm just going to go ahead and sketch them in. If it was the AP test, you always want to draw those forces the correct magnitude. All right, so that says Fn comma 1. All right, Fn comma 1 and Fn comma 2. You could have just don't need to write the commas, I guess. All right, so there we have it, right? And the next issue we have after we do the free body diagram is picking a pivot. So we would like to pick a pivot somewhere where we would have an unknown force that we don't want to have to worry about, right, for torques. So I think it's pretty obvious where the pivot should be here, but I'm going to go ahead and just point it out, right? And that's right there at the end where Fn1 is. So this is going to be my pivot. Could I have picked right here? Yeah, but this seems like the natural pivot because I know the distance from here to here to the board's force gravity. I know the distance from the pivot to here. This is 1 meter to this end of the board, so this has to be 2 if the whole board is 3. So this just makes a lot of sense to keep it there. But yeah, I mean, technically you could solve the problem with the pivot here, but you'd have to know this distance right here, which I guess we could figure out. That would be 0.5 meters. Yeah. All right. Anyways, I'm not doing that. So I'm going to put the pivot there. Okay. Next thing is balance any x forces, right? There's none. So we're going to start by balancing the y forces. I'm going to go ahead and write that just right here. So sum of the forces in the y direction. I know there's a place for me to write it there, but whatever. I'm just going to do the problem, and I wrote the NOGAT a long time ago, so I'm not too worried about it. Sum of the forces in the y direction equals 0. All right, so then our Fn1 is a positive y force, Fg is a negative y force, and Fn2 is a positive y force. Do I have to write all my positive forces first? No, but sometimes I like to do that just because it makes the problem seem easier. All right, so we don't know Fn1, we don't know Fn2, but we do know force gravity, board weighing 100 newtons, so there we go. It's already in newtons, we don't multiply by g, right? That's if they gave us kilograms of the mass, but they didn't, they already did it for us, so they already multiplied by g. So this is like a 10 kilogram board, right? Okay, so we can say Fn1 minus 100 newtons plus Fn2 is equal to 0. And that's where we got to stop, right? I'm just putting a line around this just so you can see that. It's not an answer, so be careful. In some other classes, you know, teachers, you put a rectangle around something, they think it's the answer, so watch out for that. All right, so now we're left with our next step, which is to balance the torques, right? Okay, so once again, because Fn1 is through the pivot, it does no torque. This force gravity is going to do torque. This is a 90-degree angle. This is perpendicular. This Fn2 is also perpendicular. It's a 90-degree angle. So these are going to be easy torques to calculate for both of these. And so let's go ahead and sum the torques. So the sum of the torques is going to equal 0. Which one's the positive torque here, Fn2 or Fg? Well, which one's going to cause the board to turn counterclockwise? That would be Fn2. So we can say the torque due to normal 2 is going to be positive, and the torque due to gravity is going to be negative. So it's going to look like that. All right, so the torque is equal to Rf sine 90 for both of these. So we can go ahead and say for Fn2, it's going to be the R value. What's the R value from here to here? Well, 1 meter there, 2 meters there then, right? So it's going to be, should I write I don't need to write the variables. We're fine. All right, so 2 meters times Fn2 and then times sine 90. I'm writing that out because I just want you to see it's still there. We're still thinking about that because it's not going away. Not all these problems are going to be this easy. So the next one is going to be 1.5 meters times Fg times, which I do know Fg, but I'm going to go ahead and just write that, times sine 90. Okay, let's go ahead and plug in Fg. We get rid of these sine 90s, just become 1. So we get 2 meters times Fn2 minus 1.5 times 100 equals 0. 100 times 1.5 is 150. Add it to the other side. 150 Newton meters. Over here we'll have Fn2. We have a 2 meters out in front. Divide both sides by 2 meters, so we get 2 meters here. If I'm going too fast, slow this down a little bit and convince yourself that this math is right. Because if you're getting tripped up on that math, that's a problem. So go a little slower there and show all your work. Units here. or just newtons? All right, so we are not done, right? We got to know Fn1 as well. Interesting. Will Fn1 be larger or smaller than Fn2? Do you have a prediction there? Well, this one's closer to the center of gravity, right? This one's further away. Seems like being further away, this distance is larger, so the force would get to be smaller, maybe, and this one would have to be larger, and it's closer to the center. So my prediction is Fn2 is larger. I guess that's easy. That's just a prediction, but it's easy to see if you just look at plugging this in here. I think yeah, that's easy to see how that's going to work out. All right, so let's go ahead and do it. If you can't see it, that's okay. So let's sub this in right there. Right? And rewrite that down here. So we have Fn1 minus 100 newtons plus 75 newtons equals 0. Negative 100 plus 75 is negative 25. Kick that over. All right, that's it, and that's all for that problem. So pretty straightforward. In that one, you kind of got to see these steps in action, so that was cool. We had to pick our own pivot, and do a free body diagram, right? They didn't give us the forces automatically. All right, good. Let's do another one. All right, an example problem 3. This is very similar to example problem 2, except now we have a person lying on the board, and we have a scale here on the other side, which is telling us that scale reads 250, so it's telling us the force is pushing up with here, Fn2. We do not know Fn1, and we want to find the distance to the person's center of gravity, which we don't know. Because a person isn't a symmetrical object per se, but we think we can find that because their force of gravity is going to act at their center of gravity, and it's going to contribute a torque to this system, right? And so here they even give us a hint here and say put the pivot as left side of the board. I'm not sure if that is something I wrote or if the book said that. It's probably just something I wrote. So we'll put the pivot there again at the end. Notice why, right? By putting the pivot there, which force does 0 torque? Well, any force is through the pivot, so which force would that be? You should say Fn1, right? Which we don't know, so that's going to make our life easier. Okay, now I wonder here if going right to balancing the torques is a better idea, but if you just follow the rules, right, balance the x forces, balance the y forces, or whatever order, right, but I like to do it that way, it seems the easiest, then torques, you'll solve the problem. So is it the most direct way through? Maybe, maybe not, but it doesn't really matter, and we just wanna get the right answer. So all right. So let's look at x forces. Obviously no x forces, so we don't have to balance that. Y forces here, we got, I think, 4 of them, right? The person contributes a weight, and the board contributes a weight. So let's go ahead and sum those forces. I don't know how much room I'm going to have, so I'm going to go ahead and do this. And then I'm going to start here. Sum of the forces in the y direction is equal to 0. Let's think about our y forces here. Positive here is Fn1. Fg of the person is pointed down, so we'll call that Fgp. Force gravity of the board is pointed down, we'll call that Fgb. And force normal of, Fn of the other side of the board right here, Fn2. And and that's going to be positive, my fault. All right. So that looks like what we have. We know some of these, so let's go ahead and plug in some numbers here. Fn1 we don't know. Fg of the person, they tell us, is 600 newtons. The reaction board is, I'm reading up here, is 250 newtons. And plus, oh, no, wait, we don't. Do we know the reaction board? I don't think we do. Oh, it's 60 newtons, sorry. Yeah. Okay, so, all right, let's just get rid of this. 60, negative 60. All right. And if, yeah, okay, it says right here, 60 Newton reaction board. Okay, I was just reading it from here. All right, then the scale reads 250. Now this is only reading what this, the scale reads the weight it pushes back with. And so this scale is only pushing back right here, which is Fn2, not Fn1. So we're only gonna call Fn2 250. We don't know what Fn1 is. But it looks like we're about to find it. I don't even think we have to find it. We just have to find distance, but hey, whatever, that's all good. Let's go ahead and solve it anyways. It looks like it's pretty easy. So minus, I'm just going to do this one in my head really quick. 60 plus 250. Ooh, can I do this in my head? I think you can. I think I can. What would this be? This would be negative 410. That looks right. All right, so negative 410. Can't write. Add that to the other side, that's a 4. Ugh. Add that to the other side, Fn1 is equal to 410 newtons. All right, does that matter? Probably not. I don't think we need that because I think we're gonna solve this problem with torques. And notice, even though we know Fn1, how much torque is Fn1 going to do? Well, it's going to do R times 410, but there's no R value, right? So that does 0 torque. So it's not going to matter. Oh, well, you know, I just wasted a little bit of your time. I'm sorry. But it's good for you because maybe the problem did ask for force normal 1, and you would have to be able to solve that. So, all right, let's go to some of the torques now. Some of the torques, God, that's a sigma. Capital sigma is tough to write. All right, sum of the torques is equal to 0. Let's look at these forces. How many forces contribute to torque? Well, this one doesn't, this one does, this one does, and this one does. So it looks like 3 torques. Which one's positive? Well, this one, right? Because it's going to cause the reaction board to move this way, which is counterclockwise. And these are going to be negative torques. So we're saying that the counterclockwise torque, so the torque of Fn2, right? So I'm going to write torque N2 minus torque GP minus torque GB is equal to 0. Now, is it necessary to write this? I just like seeing this because now I can, it just slows the problem down a little bit for me, and I can understand what's happening just generally, right? Before I start adding in R and F for each of these and sine 90 or cosine something, or, you know, whatever angle, crazy angle we might be dealing with. So that's why I write that. All right, so torque N2 is going to equal the force due to N2 times this distance, right, out here to Fn2. What's that distance? The distance of the board, which is, yeah, it's a 2.5 meter long reaction board. All right, so this is going to be 2.5 meters. So we're saying we have here 2.5 meters times Fn2, which we know because the scale reads 250. All right, minus the torque due to the person, The person's weight is 600 newtons. We do not know the distance from the pivot to their center of gravity, because we cannot assume for a person that their center of gravity is in the middle, because they're not a symmetrical object, right, like the board is. So we don't know this distance here. So I'm just going to call it d, because that's what we're solving for, and we'll be good with that. So we can say minus d times 600 newtons. Oh, you know what I forgot back here? Sine 90. And I'm not going to forget it here. Sine 90 minus, this is for the board now. So the distance to the center of the board, well, this is a 2.5 meter long board, symmetrical object, so that would be 1.25 would be this distance is in the middle, right? So we can say 1.25 meters times weight of the board, 60 newtons, times sine 90. Running out of room. And all of this is equal, if I can write it here, all of this is equal to 0. All right, let's go ahead and simplify here. All these sine 90s can go away. They're all equal to 1. 2.5 times 250. Oh, what is that? Is that 625? I think it is. Yeah, 625. Ooh, it's thunder. 625 Newton meters. I don't know if you guys can hear the thunder, but yeah. All right, anyways, about to storm. 625 Newton meters minus 600 newtons times D. Minus 1.25 times 60. I can't do that in my head. 75. Ooh. I probably could have done it in my head, but I didn't try. All right. All right, good. This can simplify pretty easily, right? 625 minus 75, what's that? 550, right? So we can say we have then 550 Newton meters minus 600 newtons times D is equal to 0. Kick that over the other side, it becomes positive 600. So we get 550 Newton meters is equal to 600 newtons times D. Divide both sides by 600 newtons. We want to know what D is. Looks like it's going to be smaller than 1. Notice these newtons are going to go away. It's going to be smaller than 1. Does that make sense? I don't know. Let's get the answer first, then we'll think about it. 0.9167, 0.927, no, 0.917 or 0.92. I'll just go with 0.92. So that is the distance to the woman's center of mass. Let's think about that. So if it's 0.92 meters, would that make sense? Well, this is, the distance to here is, we're saying is 0.92 meters. Well, the distance to here is 1.25, so that's reasonable. Yeah. All right, so, okay. There's our answer right there. Good. Hopefully there's no questions there. It's pretty straightforward and similar to the last problem, but a little more complicated. All right, so now let's step it up again and go to a problem that's even a little more difficult. And I think this one, I'm going to get a separate sheet of paper for this diagram because we're going to have to draw this. And then I'm going to need some room to calculate. All right, so I'm going to pause it there and get that piece of paper. All right, so let's look at this next one. This is example problem 4. It says a 3-meter ladder. Let's draw this. So it's going to look like something like, it's going to be 60 degrees for the angle to the wall. So we have this 3-meter ladder. I'm sure this drawing isn't going to be great, but it's okay. the best I can do. And this angle right here. Oh man. Putting holes in this paper. This table I'm writing on has these little grooves in it, so easy to ruin a piece of paper. All right, this is 60 degrees. I think that's pretty reasonable. Maybe it should be a little higher up. Maybe this is closer to 45 based on the looks of it, but oh well, it's what I got now. It's supposed to be 60. All right, so this ladder is 3 meters, right? All right. That's good. It says 60-degree angle with respect to the floor. What is the minimum value of mu static, the coefficient of static friction with the ground that will prevent the ladder from slipping? All right, so we want to know what mu static is. So that means there's going to be a force of static friction, right, to keep this ladder stationary, because we don't want the ladder to slide. Now, we're going to have to draw some forces. There's some hints there for us. I'm not going to read those yet. But let's just think of it the same way we did previous problems, right? We have extended object. We start with a free body diagram drawing some forces. Okay, so, all right, what can we do here? Well, let's think about possible forces on this ladder. Probably the most obvious one, right? If we find this symmetrical object being a ladder, so if we find the center of the object, we can draw from the center of mass here the force of gravity of the ladder. Now in the homework problem for this, there's going to be a person on the ladder. So if there's a person on the ladder, then the person, let's say they're up here, would also have a force gravity here. And so it just makes the problem a little more complicated because you'd have 2 force gravities to deal with at different points from the pivot. Where should the pivot be? Well, I think it's going to be obvious in a second. Other forces here, friction, right? Now, we're assuming, this problem says, assume there's no friction with the wall. And we'll talk about that in a second, but let's talk about the floor. So the ladder wants to slide how, right? The ladder doesn't want to go in like this. The ladder wants to go out, right? The ladder wants to fall like that. So if the ladder wants to move this way, friction should point the opposite, right? So we're saying that at this point right here, down at the bottom, there should be a force pointed in like this, called force friction static. All right, that's pretty tricky. But also at this point, there should be a force pointed up. And what force is that going to be? What would the floor push back on the ladder with? Well, we'd say force normal, right? So I'm going to go ahead and call that force normal of the floor. Now you might be saying, well, what about up here? All right, well, what about up there, right? So first of all, is there a frictional force up here? Yes. If it was a more complicated problem, which way does the ladder want to slide? Let's think about it. It wants to go like this, so friction would point which way. If the ladder wants to move this way, we would say up, right? So, but we don't have that in this problem. They didn't give us that mu value. We're not worried about it. They say ignore friction with the wall. It says it right here. Friction between the ladder and the wall is negligible. Okay, so no upward friction there at the wall, but the wall does contribute this. What's this? Well, it's similar to the floor, right? It's a surface pushing back. We call that a normal force. Okay, and that's it. So we got 4 forces to worry about. Next step, after we draw the free body diagram of an extended object, right, with the forces acting at different points, the next step is to pick the pivot. Where should the pivot be? Well, somewhere that eliminates an unknown force that simplifies the problem. Well, all right, I think it's fairly obvious where that could be, based on the fact that the ladder has 2 unknown forces acting right here. it would make sense, I think, to put the pivot right there at the bottom. So let's go ahead and do that. So we'll call this point the pivot down here. I'm just going to write that in right here at the bottom. And notice we picked it, right? Once again, you pick a different pivot, the torques change, but the sum of the torques will still equal 0 regardless of what place you pick as a pivot, because the object is in equilibrium, right? Like this ladder's sitting there against the wall, and I pick the pivot here, and you pick the pivot here, and another student picks the pivot here. The ladder doesn't care where you guys pick the pivot or where I pick the pivot, right? The ladder's still going to be sitting on the wall in equilibrium. So does the pivot change the torques? Yes, but the sum of the torques is still 0 because the ladder is just going to sit there, assuming it's in equilibrium. All right, so anyways, let's go ahead and start summing the forces. X forces, we finally have X forces. All right, so once again, you know, when I'm summing the X and Y forces, I've been doing this without stating it, but I'm calling positive X right, I'm calling negative X left, I'm calling positive Y up, I'm calling negative Y down. All right, so anyways, some of the X forces, I'm going to get a little, no, I can probably work right here. And we want to know mu S. Okay, that's our goal here. All right, so sigma Fx equals 0. All right, positive X forces, force friction static, negative X force, Fn wall. All right. Okay, I don't think we know either of these, so I'm just going to take it a step further. You might say, well, don't we know force friction static? Because I kind of stopped there, so I put that square around it, or rectangle. Don't we know force friction static is equal to mu static times Fn? This would be Fn floor, right? Yeah, we do know that. So I guess we could go a step further. Look where this is taking us. This is interesting. All right. So what I got from there, right, by using that trick, that knowing that mu S is equal to force friction static, I could have just wrote FFS. All right, but whatever. Force friction static, mu equals force friction over Fn, right? Force friction equals mu Fn. Mu equals force friction over Fn. Utilizing that. So that's what we have here, I believe. Yeah, I have mu, force friction static equals mu Fn. So, all right, so what I did here, I'm trying not to confuse people at the same time. So this is actually what I did below, is I used force, I rearranged this one more time to get this, right? And this is what I ended up using. So once I had this, mu static, I plugged this in, mu static times Fm. These are the same, right? I plugged mu static times Fn in for this right here. So I had mu static times Fn for force friction static is equal to Fn wall. All right, hopefully that wasn't confusing. It was only confusing because I wrote that. I'm sorry, I shouldn't have wrote that. That was bad of me. All right, so this relationship right here was utilized right there by subbing in mu static times Fn for this, and that got me to here, mu static times Fn is equal to Fn wall, and then rearranging for mu static. This formula is not the same as that one up there. That's all about the floor. This one has the wall and the floor. This is totally different. All right, this is not a generic formula. This is just based on the problem. Okay, so we're seeing that for this problem, this relationship holds true if the ladder is in equilibrium. This is true for any problem, and so is this, but that's for one surface. Okay, so great. All right, a little bit of a tangent there. All right, so if we can find, using the y direction and the torques, if we can find Fn wall and Fn floor, I think we know mu s, and that's our goal here. All right, so let's go ahead, whoops, let me get this out of the way. Let's go ahead and find the sum of the y forces, right? I always like going there next. Okay, what are my y forces here? It looks like I have two of them. Okay, FG ladder, do we know it? I don't know. Let's go back to the problem and look. It looks like that's a no, which is kind of lame because you'd think they'd have to tell us that. Just tell us a 3-meter ladder. Not a lot of help. That's great. All right, so let's go ahead and go a step further here. We can then say that Fn floor is equal to Fg. Interesting. All right, but we don't know what Fg is. We do know, I guess we could write it this way. All right, Mg. I'm not sure if that's going to help us, though. I think we're kind of stuck there. Thanks a lot, y direction. All right. So now let's go to the torques. Let's go down here. Okay, so what's going to contribute to torque? And this is where picking that pivot is going to help out a ton, right? These we don't have to worry about for torques because they both go through the pivot. This does not go through the pivot, right? Pivot's over here. This one does not go through the pivot, right? That line will never hit this pivot. So both these are going to contribute torques. And unfortunately, I know you don't want to hear this probably, but we're not going to be able to use sine 90, right? If the force gravity pointed this way, we could use sine 90. If the force Fn wall pointed this way, we could use sine 90, but it doesn't. So we're left with two ways of thinking about torques. We either find the perpendicular force, right, of Fg would be here. We can find this component, and the perpendicular component of... All right, so I got cut off there. But what I was trying to say is we could find the perpendicular component of Fn, and that would, you have to use some sine or cosine for this angle. But I think it might be easier if we use r perp. Here's r, this distance to force gravity, which is 1.5, right, because it's half of the ladder. And this distance from the pivot to the wall or the end of the ladder would be 3 meters. And the way we would find r perp on both of those, I think might be the easier way, which is extending the force line. So I'm thinking that's what we'll do. And if we start here by just, I guess, recognizing what kind of torques they're putting on the ladder, right? Force gravity is going to cause this ladder to torque this way, which is going to be a negative torque because it's clockwise. And force normal is going to put a counterclockwise or positive torque. So I'm saying that down here, then we have the torque from the wall, or I could put force normal wall. I forgot. Yeah, that's what we called that. You get the idea. Torque wall minus torque due to gravity. And once again, if there was a person on the ladder, we would have an additional torque from the person's weight as well due to gravity. All right, is equal to 0. So then we have to we can say, well, to do this torque problem, right? I think it's easier to find the r perp. So here's r. Let's start with the force normal wall. Here's r, which is 3 meters. There was something. The way to find these was to draw the force, right? But then to continue to dotted line the force, right? And this was called the, this dotted line, I think, was called the line, let's call it the force line, or you can call it the line of action. And then the moment arm was found from this, which was the shortest distance, which was our perp, the shortest distance from the pivot to the line of action, right? And that is this right here. So this is our perp. So this is R, this is 90 degrees, this is 60 degrees, so what's this angle then, 30? Yeah, that's going to be 30. And so this angle up here is going to be 60. So we can see then that our perp is an opposite, right? Here's 90, here's my hip of 3. This is opposite 60 degrees, so our perp is an opposite. Okay, why does that matter? Well, torque from the wall is equal to the force normal, comma, wall, times our perp. Well, what's our perp? Well, it is R, it's opposite, right? So it's going to equal the hip sine 60, right? Because this is an opposite. So it's going to equal 3 sine 60. So down here, we can write that in as 3 meters sine 60 degrees. Force normal, comma, wall, times 3 meters sine 60. Minus the torque due to gravity. Okay, that's going to be Fg also times R perp. This is a different R perp, so I guess I could call this R perp 2. I don't know, I'm just making something up, right? So or I could have called it R perp G. All right, anyways, for this, yeah, so I keep getting cut off by my phone. It doesn't like me making videos today. All right, so for this one right here, we can see that the R perp 2, right, is going to be, here's my force line or line of action, right? Just extending this out. What is the shortest distance between the pivot and this line? Well, it's right here, right? So this is R perp 2, and here is 90 degrees. And now we can see that R is right here, so here's my hypotenuse. R is going to equal, R is only going to equal 1.5 because it's just that right there, right, is R. So we can see then that R perp 2 is adjacent to this 60 degrees. Everyone see that? That's adjacent, right? Here it was opposite up here. It was across from 60. Here it's next to 60. You might say, well, it's opposite 30. Yeah, sure. So you could use sine 30, but we're not. We're going to use cosine 60. And that means the complement, co means the complement angle sine, right? So that's kind of, that's where it comes from, and that's why that makes sense. So the cosine of 60 is equal to the sine of 30, right? Okay, so anyways, I'm going to use cos 60 for R perp 2. So it's going to equal the hip R 1.5 times cos 60. All right, so let's go ahead and put that in. So down here we have Fg, let's see, minus Fg, which I don't think we know, right? We said we don't know that. Times 1.5 cosine of 60 degrees. All right, and then that is equal to 0. All right, good. Okay, let's see where that can take us there. So now we can say Fn wall is equal to 3 sine 60. Sine 60, let's see, cosine cosine of 60 is 1/2. So sine 60 is at 0.866. So 3, And I hope I'm in, nope, I'm in radians. Dang. All right, let me switch that real quick. Get into degrees. All right, so 3 second sine. 3 sine 60 is about 2.60. We have the force normal of the wall, which we don't know, minus force gravity, which we also don't know, times 1.5 cos 60, and cos 60 is going to be the nice one, is going to be 1/2. So half of 1.5 is 0.75. Okay, I can type it in really quick if you like me to. 0.75. All right, and then we can go ahead and take this a little further. So maybe kick this over to that side. Let's do that. So we have 2.60 meters times the force normal of the wall, and setting it equal to 0.75. This is also meters. I got to watch my units. 0.75 meters times FG. All right, that seems like we're kind of stuck there, which is not good. So let's see if we can reconcile this somehow. So coming up here, we said that the force normal of the floor is equal to mg, right? Down here, we're saying that Fn wall is equal to 0.75 times mg. Ooh. And we notice up here that mu is going to solve by force normal wall, which we could get from here, and force normal floor. I think I'm seeing it. Are you seeing it? All right, let's go ahead and simplify this for force normal wall. So we're going to get something for wall to sub in here. We're going to get something for floor to sub in here. Yeah, all right, and they're both going to be in terms of FG or MG. That's interesting. All right, we'll turn it into MG, and then that way I think it might look a little better. All right, so anyhow, I'm going to solve this for force normal wall. So Fn wall is equal to 0.75 meters. I'm going to turn this to mg over 2.60 meters. Then we can do the math here, right? Canceling away those meters. That's tricky. Those are meters. That's mass. Okay. Let's type that in. Divided by 2.6 is equal to 0.288. All right. You guys hopefully can start to see what's going on or what's happening here. All right, so we're going to sub this in, 0.288 mg, in for the force normal wall. We're going to sub in Fn floor, just mg, so it's going to look like this. See what's happening? Why didn't they give us the force gravity? It doesn't matter. Oh, cool. That's cool. A little sneaky, but makes for a good problem. And there's our mu static friction, 0.288. All right. Would it have been a much easier problem if they just gave us force gravity? Yeah, but you might not have seen how force gravity just cancels away. And all that matters or I guess we can say that mu static is not affected by forced gravity, which makes sense, right? Mu static is something that is unique to two surfaces, and from that point of view, it shouldn't be affected by forced gravity of the ladder. If you had a heavier ladder or whatever, as long as it's the same material ladder and same material floor, mu static should be the same. Okay, so that's it. The problem I'm going to have you do after this, there will be a person on the ladder, so just one additional torque due to the weight of the person, and then obviously an additional Y force as well due to the weight of the person pointed down. Torque from the person would also be a negative or clockwise torque, but that's about it. I think for this note guide. And yeah, if you have any questions, let me know. And hopefully when I put all these videos together, it's not too annoying with all the stopping and starting I had to do with